Welcome to AI Paper Podcasts. Imagine trying to teach a robot how to, delicately place a fragile object. Now, usually this takes a ton of work, right? Hundreds of human demos, often using complex setups like teleoperation.
Yeah, it's painstaking.
But what if you could just show it one video of a person doing it, and the robot learns from that? Well, that's the core idea we're diving into today with this paper called Human-to-Sim-to-Robot. It's about this new framework where robots can learn tricky manipulation skills just from a single RGBD video of a human.
It's pretty cool. They use this real-to-sim-to-real reinforcement learning approach.
Right. And it kind of cleverly bridges the gap between, how a human looks and moves and how the robot's actually built.
And crucially, no special wearables on the person. No massive data sets needed.
So they basically pull out two key things from that video: how the object moves, that trajectory, and the hand pose right before the action starts.
Exactly. And those two pieces guide the robot's learning process in simulation.
And the results? Well, they say it outperforms other methods and works for a whole bunch of tasks: grasping, pushing, even multi-step stuff.
It's a really elegant approach, honestly. It tackles a major headache in robotics, getting all that high-quality demonstration data.
Yeah.
Think about the time saved if you can just film someone instead of, spending hours doing teleoperation. This paper is a really compelling step forward.
Okay, so let's break this down. The old way, imitation learning, often meant guiding the robot or using those complex setups you mentioned.
Yeah.
Why is it so hard to just use a human video directly for robot actions?
Well, there are a couple of big challenges. First, like you said, collecting tons of robot demonstrations just isn't practical for many tasks. It's super time-consuming, needs special gear, special skills.
Right.
Second, even with a human video, it doesn't directly tell you the robot's commands. You see the human hand move, but the robot needs specific joint instructions.
Yeah, the robot's got different muscles and bones, so to speak.
Exactly. So a common workaround is trying to estimate the human hand's 3D pose from the video, where it is, how it's oriented, finger positions, and then use something called inverse kinematics, or IK, to figure out the robot joint angles to match that pose.
But that doesn't always work perfectly.
No, it runs into issues. Hand pose estimation can be inaccurate, especially if the hand is partly hidden or the video's noisy. And even if you could get a perfect human pose, the robot might not physically be able to make that exact shape or movement. What's easy for us might be impossible or really unstable for a robot arm and hand.
Especially for those really fiddly, contact-rich tasks.
Precisely. Things requiring fine fingertip control, direct mimicry often just breaks down.
Okay, so that brings us to Human-to-Sim-to-Robot. Let's get into the framework. How do they create this virtual practice space, this digital twin, without a massive effort?
Yeah, this part's surprisingly straightforward. They use off-the-shelf 3D LiDAR scanning apps, stuff you can get on your phone or tablet.
Like just regular apps?
Yeah, things like Curie Engine or 3D Scanner app. You just walk around the object you want the robot to handle, scan it, scan the scene around it. Takes maybe a few minutes.
Wow.
And boom, you've got these 3D mesh models that you can just drop into their simulation environment. In this case, they used Eyes at Gym.
That's like taking a quick 3D photo with your phone.
Yep.
Okay, so they've got the virtual world, and they have the RGBD video that's color plus depth info of the human doing the task. How do they figure out how the object is moving in 3D?
Right, because the video itself is just, video. They use some really smart AI tools here. First, an open source model called SAM2 Segment Anything Model 2.
Okay.
SAM2 is great at picking out objects. So it creates a mask, like an outline, of the object being handled in every single frame.
Got it.
Then they feed these masks, along with that 3D object mesh from the scan, into another open source model called Foundation Pose.
Foundation pose.
Yeah, and Foundation Pose uses that info to estimate the object's full 6D pose, its 3D position and 3D orientation throughout the entire video. So they reconstruct the object's 3D journey from the flat video.
Okay, AI models giving the robot eyes to track the object in 3D. Cool. What about the hand? That initial pre-manipulation pose. How do they nail that down?
They use another model for this called Hamer. It's designed to estimate 3D human hand pose from just a regular RGB image.
Okay.
Now, Hamer is good with the shape and orientation, but the depth might be a bit off, so they refine it using the depth data from the RGBD video.
Using that extra D.
Exactly. They use SAM2 again to mask out the hand, get the 3D points for the hand from the depth sensor, and then use an algorithm called ICP, Iterative Closest Point, to sort of nudge the Hamer pose until it lines up really well with the actual depth data.
So combining AI vision with the depth info gets a pretty accurate accurate 3D hand pose.
Yep, much more accurate.
But how do they pinpoint when this pre-manipulation pose happens? It's not just any random point before the action, right?
Yeah. Right. They define it based on when the object starts moving significantly. They track the object's speed in the video. As soon as its velocity goes above a small threshold, they used 5 centimeters per second.
Okay.
That's considered the start of the manipulation. The pre-manipulation hand pose is then the hand pose exactly 10 frames or time steps before that movement starts.
Capturing the moment just before contact.
Precisely. It captures how the hand is shaped right as it's about to interact. From that 3D pose, they grab the key points, fingertips, base at the middle finger.
And then this human hand info has to be translated to the robot hand, which, as we said, is different. How do they do that retargeting?
They use a 2-step IK process with a library called QRobo, first step. Get the overall arm and hand position right. They adjust the robot's arm joints so the base of its middle finger lines up with where the human's middle finger base was, maybe with a small offset for size differences.
Okay, general positioning first.
Second step. Once the base is aligned, they fine-tune the robot hand's internal joints to get the robot fingertips as close as possible to where the human fingertips were estimated to be.
So it's not a perfect copy, but it's inspired by the human approach.
Exactly. It gives the robot a reasonable starting configuration in the simulation, even with the embodiment differences.
Okay, so we've gone from a real demo video to a sim environment with a target pass for the object and a starting hint for the robot's hand.
Oh.
Now, how does the robot actually learn the task in the sim?
Yeah.
You mentioned reinforcement learning, PPO.
Yep. So inside as a gym, with the digital twin of the robot, the scene, the object, they train a control policy using PPO proximal policy optimization.
Okay.
The robot's goal isn't to copy the human's exact joint movements. Instead, it's learning how to move its own arm and hand to make the object follow that 6D pose trajectory extracted from the human video.
So focus on the object's outcome.
Exactly. It learns by trial and error. It gets a reward based on how closely the object's pose in the simulation matches the target pose from the human demo at that moment in time.
And what does that reward function look like? How do they measure how close?
The reward, R equals RobJT, is basically the exponential of the negative relative pose distance. So the smaller the distance between the object's current pose and the target pose, the higher the reward. The exponential shape really pushes it to get close quickly and then stay close.
Makes sense. And in this relative pose distance, it has to consider both position and orientation, right? Not just location.
Absolutely. They calculate it using a few anchor points fixed on the object in its own coordinate system, usually 3 points, one along the x-axis, one y, one z, at some distance L from the center.
Okay.
The distance is the sum of how far apart these corresponding anchor points are between the current object pose and the goal pose. That L value kind of tunes how much orientation errors matter compared to position errors.
Ah, clever. So you can adjust L based on the task.
Yep, or even change the anchor points if the object has symmetries where rotation doesn't matter as much. It's flexible.
Very neat. So what info does the robot actually get in the sim to make decisions? What are its senses?
Its observation space is pretty comprehensive. It gets its own joint angles and velocities, the 3D positions of its fingertips, the center of its palm, and crucially, the 3D positions of those anchor points we just talked about, both for where the object is and where it should be according to the goal trajectory, gives it a good picture of itself and the object relative to the target.
And what actions can the robot take? What levers can it pull?
The policy outputs a few things: a target 3D position for its palm center, a target 3D orientation for the palm, usually as Euler angles.
Right.
And then instead of direct joint commands for the fingers, it outputs target values for the main ways the hand can shape itself, derived using PCA principal component analysis, usually the top 5 and PCA 5.
TCA values, so it's controlling the overall hand shape.
Yeah, these higher level commands then go into something called a geometric fabric controller, which figures out the specific joint movements needed. It allows for more coordinated hand motions.
Gotcha. High level goals, lower level execution.
Yeah.
And they initialize the robot near that pre-manipulation pose.
Yes, but not exactly at it. They use that retargeted pose as the center of a distribution for the starting state in each training episode. They add random variations to the hand pose, even the object's starting position.
Why add noise?
It forces the robot to learn a policy that's robust, one that doesn't just work for one perfect starting setup, but can handle slight variations, encourages exploration too.
And to make sure the sim learning transfers to the real robot, they use domain randomization.
Absolutely essential for sim to real. During training, they mess with the physics and the sim changing friction, object mass, inertia, even adding random pushes to the object.
Making it learn to cope with unpredictability.
Exactly. It makes the policy less brittle, less dependent on perfect simulation physics, and more likely to work in the noisy real world. They also use an LSTM policy.
LSTM, that helps it use past information.
Right. It leverages temporal context, which usually leads to more robust control. And importantly, they train using the object's pose information directly, not simulated camera images.
Why is that better?
It avoids the reality gap issue with visual appearance. The policy learns based on geometry, making it less sensitive to differences in lighting or textures between sim and real.
Okay, so after all that sim training with randomization and pose data, they just deploy it straight onto the real robot. Zero shot.
That's the claim. Zero-shot transfer, no real-world fine-tuning.
And how does the whole system run on the physical robot then?
It's a pipeline. First, you have the real-world camera feeding images to foundation pose, which tracks the object's 6D pose at about 30 hertz.
Okay, tracking the object live.
Then, the trained RL policy takes that pose estimate and decides on the next action target palm pose. PCA values running at around 15 hertz.
Slower than the tracking.
Yeah, the policy inference takes a bit longer. Those actions go to the geometric fabric controller running faster at 60 hertz, which calculates the target joint positions.
Got it.
And finally, a low-level PD controller on the robot executes those joint commands at a really high rate, like 200 hertz, actually moving the motors.
Quite a cascade. Okay, so the paper backs this up with experiments. What did they find? How important was this specific RL approach compared to simpler things?
Yeah, the validation was pretty thorough. They tested it on 7 different real-world tasks, pushing things, pouring from a pitcher, pivoting, even multi-step stuff like lifting and racking a plate.
Good range.
And they compared human to Sim2 robot against several baselines, like just replaying their retargeted human joints, or an object-aware replay that tried to adjust the start, and even behavior cloning, training a policy to directly mimic the retargeted human motion.
And how did human to robot do?
It significantly outperformed them. Success rates were much higher, like 67% better than simple replay, 55% better than the object-aware replay. It even beat behavior cloning.
Wow, that's substantial. Why did the other methods fall short?
Well, the replay methods are open loop. They just play back movements. Any small difference in the real world, and they fail.
Right, no feedback.
The object-aware one helped a bit, but still suffered from inaccuracies in the initial hand pose estimation and that fundamental human-robot embodiment gap. Behavior cloning, trying to learn from just one noisy, retargeted demo, even with augmentation, likely just didn't have enough good data to generalize robustly.
Whereas the RL approach learned a strategy tailored to the robot.
Exactly. It wasn't just rigidly copying. It was learning how it could best achieve the object's goal trajectory, leading to more adaptable and successful behavior.
Did they also test why specific parts of their method worked? Like, did using the full object trajectory as a reward really matter?
They did. They ran simulation ablation studies. They compared using the full trajectory reward to simpler rewards, just the final goal pose, or just interpolating between start and end, or using a less frequent trajectory update.
Yeah.
Using the full dense object trajectory consistently led to faster, more stable learning and better final policies. That continuous feedback really helps guide the learning process effectively.
Okay, so the detailed path matters. What about starting the robot near that human pre-manipulation pose? How crucial was that?
Also very important, it turns out. They compared initializing near the pre-manipulation pose to starting in a default neutral pose, or way up high, or even further away.
And the human-inspired start was best.
By far. It gave the robot a much better starting point, helping it find good solutions faster. Starting from other, less relevant poses made learning much harder, sometimes leading to policies that got stuck in bad strategies. It really helps bias the exploration towards useful interactions.
That makes intuitive sense. Guide the exploration bit.
Yeah. And interestingly, they saw the robot sometimes find different ways to do the task than the human because of its different hand structure, but still succeed. Like a human might lift a plate using certain fingers, but the Allegro hand might learn to use a different combination that's more stable for it.
That really shows it's learning the goal, not just mimicking blindly. Did they find that just the single pre-manipulation pose was enough? Or did they need the whole hand path?
They tested that too. They compared just using the pre-manipulation pose for initialization versus actually adding a reward for tracking the entire human hand trajectory or trying to learn a policy that just corrects the retargeted human motion.
And the single starting pose was sufficient.
Yes. Turns out, trying to reward tracking the whole human hand path actually slowed down learning. The robot got distracted trying to copy hand movements that weren't necessarily the best way to move the object, and the correction approach suffered from noise in the base trajectory.
So focus on the object goal, use the initial hand pose as a good starting hint, and let the robot figure out the rest.
Pretty much sums it up. It's a more robust way to learn from that single demo.
This is incredibly cool stuff, but like all research, it has limits. What did the authors say about future work?
They acknowledged a few things. Most testing was done with one specific robot set up the Allegro hand and a particular arm. So exploring how well it works with other robots, like maybe simpler grippers, is needed.
Makes sense. Generalization.
Also, it's focused on single object tasks defined by a pose trajectory. Handling multiple objects interacting, or tasks in more cluttered spaces, is a clear next step.
Yeah, multi-object stuff is way harder.
And the method relies on good object tracking and a decent rigid body simulator. So dealing with objects that bend or deform or articulated objects would require better tracking and simulation tech.
Right, soft bodies are tough.
Finally, the pose estimator itself can struggle with things like perfectly symmetric objects where orientation is ambiguous or really shiny reflective objects. They suggested ways around that, like changing the anchor points for symmetry or maybe training an image-based policy to handle reflections better.
Okay, so lots of interesting avenues still to explore, but fundamentally this seems like a really promising direction for making robot learning easier.
Definitely. It's a big step towards making it more scalable, teaching robots complex skills just by showing them once. That opens up a lot of possibilities.
So to wrap up, the big takeaway from Human to Sim to Robot is this novel framework, Real to Sim to Real RL, that lets robots learn dexterous skills from just one human video.
Yep. By cleverly extracting the object goal and a starting hand pose and using simulation tailored to the robot, it bridges that tricky human-robot difference without needing tons of demos.
It really makes you wonder, doesn't it? If teaching robots becomes this easy, what kinds of things could we see them doing soon? In factories, warehouses, maybe even helping around the house or in healthcare.
The potential is huge. It could really accelerate robot deployment in complex, real-world scenarios.
Definitely something to think about. For all you listeners wanting the full technical details, you should definitely check out the paper itself. Just search for Human to Sim to Robot.
It's a great read if you're into robotics or AI. Lots of good detail in there.
Thanks for tuning into this episode of AI Paper Podcasts.